Freeform micro-optics have the capabilities to revolutionize industries. Imagine automotive lighting that is perfectly aligned with the design of the car, or lighting solutions that provide better energy efficiency, better light distribution, and perfect aesthetics. Imagine all AR and VR capabilities with better resolution, feeling more realistic, yet the device reduced to a size that you don't even realize you are wearing. Or improving your home with luxury and smart windows. That is the power of Freeform micro-optics. The ability to create optical shapes in any form you want, completely miniaturized for perfect integration. Opening up new opportunities for security and branding, optical communications, consumer electronics, and more. And now imagine that this can be done with equal or even better specifications than conventional systems, and at lower costs. This is why Fabulous has opened up the one-stop shop in Freeform micro-optics, making this technology now easily accessible to everyone who wants to implement it, proving a full supply chain of world-class Freeform micro-optics specialists. We can take you from design to prototyping and into pilot production. For full product lifecycle, including design, modeling, origination, tooling, and manufacturing services. Some have already paved the way by integrating Freeform micro-optics into their product portfolio. Are you ready to take the next step in your product development? Make it fabulous. And contact the one-stop shop for Freeform micro-optics at info@fabulous.eu. We are fabulous.
So good morning, everyone. I'm Jörg, Technology Manager at Epic, and I'm really pleased to moderate this fabulous workshop for today and tomorrow morning. So we'll talk and learn about Freeform micro-optics technologies through highly relevant speakers from companies covering all the supply chain of micro-optics, from the design to the application, including fabrication. So the aim of this workshop is for you as participants to get the maximum information of Fabulous and get answer if you have some question. So we will have technical presentation today, but we plan also a networking and Q&A session at the end of this workshop, where you could discuss and exchange with the participants, but also ask any question you will have regarding Fabulous. We have Jessica Van Eyck in the room with us today. She is the Managing Director of Fabulous, so she can give you all details you need regarding the project. So this workshop is organized on 2 mornings. So today's morning will be focused on extended reality market, which include augmented and virtual reality technologies. And tomorrow morning, we'll talk about Freeform micro-optics for automotive market. So we'll have in global 13 relevant speakers on these 2 mornings. Why did we decide to focus this workshop on these 2 markets? Firstly, the XR market. So this is and will be one of the most dynamic market for the next decade with an important CAGR. Photonics technologies are one of the pillars of extended reality. And while talking about it, if you're interested or curious about how we use photonics in this industry, I invite you to read the article we published in Photonics Views related to photonics for XR market, and we'll find more details also. Automotive lighting, so a market in constant growth and really solid, and was one of the most promising market for photonics in automotive industry, with more than 30 billion estimated market in 2025. The lighting signature is now a strategic way for companies for differentiation as well as for autonomous vehicle, so which will be really predominant in the near future. Just a quick view of few use cases of Fabulous in ARVR and automotive market. LIMBAK, so we'll have a presentation from LIMBAK later this morning. So here it's a thin-free from optical lenses with improved image resolution and reduced volume and field of view for ARVR headset. Micro OLED, so also we'll have a presentation this morning by Xavier Bonjour. We will present the product of Micro OLED Active Look, the AR product. So the technology developed by Micro OLED provides brightness enhancement and control of angular light emission for wearable AR systems. And HELA for automotive market. So this is a headlights using Freeform micro-optics with a uniform appearance in the on-off state. A view on the agenda of this morning. So we'll have a presentation by Jessica Van Eck, presentation for fabulous presentation. Two sessions this morning. First one about design and fabrication. So we'll have a presentation by Bharath Rajagopalan from STMicroelectronics, Mathijs Meulen from Morphotonics, Ruben Mohedano from LIMBAK, Guillaume Tison from Imagine Optics, and later this morning we have a presentation from Jörg Reitterer from TriLite, Yuka Perento from Imprint, and Xavier Bonjour from MicroOLED. And we will end this morning by a networking and Q&A session after 11 this morning. And just a quick view of the program for tomorrow morning for automotive. So a presentation by Rainer Fodisch from Synopsys, Mark Schnipper from SUS Microoptics, Marina Postnikova from Phasix, and Mark Siller from Glowing, Hagen Schweitzer from Dr. Optics, and Paul Mata from Volvo Cars. And we'll have also a networking and Q&A session tomorrow morning. So thank you very much for participating to this workshop. Here you can find our contacts. So my contact and the contact of Jessica Van Eck, Managing Director of Fabulous. So please, if after this workshop you have question, please contact us. We will be really pleased to answer your question. Thank you very much. And now, Jessica, if you want to share your screen and start your presentation.
Yes.
Thank you.
Yes, I have a question. Are you going to send us the presentations later?
Yes, some of them, yes. It depends on the speakers, but
okay.
All of them that they will agree, we will send the presentations, yes.
Thank you.
Yeah, so yes, welcome everybody, and thank you so much, Jeremy, for the nice introduction. So my name is Jessica Van Eck, Managing Director of Fabulous, the European pilot line and one-stop shop for the manufacturing of freeform micro-optics. And today we are here to talk about freeform micro-optics for ARVR. So looking at the ARVR market, we see that the market is looking at some challenges. So the size reduction, miniaturization is something that we see is something that is being focused on the field of view, the resolution, contrast, and also price. And for this, freeform micro-optics could be very interesting because it's combining the strength of freeform optics together with micro-optics. So being able to make any kind of shape, but miniaturized for easy integration and miniaturization. And we see also that there's an increasing interest, and therefore Fabulous was also created. So it's the European pilot line. And so what we do is we offer accelerated innovation, manufacturing services, and really anything you need. So if we take a closer look at those services, then you see that we can do modeling, origination, tooling, materials, quality control. So anything you need from the design up to the actual manufacturing. So we do that over 3 pillars. We have a partner for the wafer scale manufacturing, roll to plate and roll to roll. Then we can support you with the integration. And as Fabulous was funded, was created as part of the Fabulous project, we've already been running for 2 years with use cases. So we have use cases in solid state lighting, transport lighting, automotive lighting, AR/VR, micro displays, and luxury. So tomorrow I will say a little bit more about the automotive lighting, but today I see that Jeremy also told already a little bit about it, and we will hear more about it. But I thought it would be good to highlight indeed LIMBAK as one of the use cases. So they are developing high performance and innovative optics for AR, VR, MR, and they're also licensing these optics. So you can find more information about it also in the handbook. So it's good we share the presentations. I put a link here, so you can take a look at that. There's a detailed description about this available in the handbook, which also is showing all the services that Fabulous is offering. Then indeed for the micro displays, we have MicroOLED. So they design, develop and manufacture high performance micro displays. They're now using the freeform micro lens arrays to improve on the pixel luminance. So this is, of course, also very relevant for AR. I'm sure Michael OLED will say a little bit more about it. And then, of course, we have all these services that we can offer. So we have, we can support you with the design, the prototyping, the replication, integration, all of this through a single entry point. And this is very unique because, without Fabulous, you would have to, as a customer, find your company for the modeling, for the origination, for the tooling, for the integration, for the replication. And now you can go through single entry point and have all those services through a single entry point, which is really meant to make it easier to access this technology that's offering these innovative solutions. And to boost that even more, the European Commission even decided to fund European companies, even some countries beyond, to implement freeform micro-optical components into their system. So there is an open call right now running. So it's open to all European countries, some countries also outside of Europe. If you wonder if your country would be eligible, please contact me. There are fundings available up to 90%. This has to do also with your company size, and the open call will run continuously, and we will have cutoffs in March, June, November this year and next year. That means the next cutoff, I made it blue, would be June this year. And more information can be found on the website, but always feel free to contact me. I would love to discuss also about your application before you submit your final proposal. And this is, of course, open to all markets. So not only AR/VR, but all the different markets where freeform micro-optics can play a role. And so to conclude a little bit about Fabulous is, so we are the single entry point to access design and manufacturing services. We are access to Europe's leading companies and research institutions, and we really want to promote also the capabilities, because freeform micro-optics can really play a big role. And so we want to advocate that, and for that, we also launched a ecosystem/marketplace. So that was launched end of last year. And that showcases an extensive product offerings for freeform micro-optics. And that is open to all suppliers. So we really want to be able to be this single entry point that even if you wanted, you could build your own supply chain, and also for us to see which partner could maybe complement our offerings. So the aim is really to become the main source for orientation towards the implementation of micro-optics. So we just started that last year, but you can see already from the organization registry that is available that we already have many more partners on board than we currently have as members. So their offerings can also be found. There's a filter available in the marketplace. So if you select the filter for AR/VR, you can see there are different offerings of members, but also of non-members for this market. So, if you're interested in using micro-optics, then take a look also here. And then, of course, me and Tom are running the front office. So we are here, if you have questions about applying for our services or the open call to join the ecosystem, I would really appreciate it if you contact us, follow us. So all the information is here. And with that, I want to say micro-optics is fabulous. Big thank you to not only our members, but to all the partners in the project, and to the Commission and Photonics 21 for the funding. And thank you so much for your attention. Any questions?
Thank you, Jessica. Okay, we have a question from Tampere University. I don't know the name. Do you want to ask your question by yourself, maybe? Alperen, Aidin, if you want to ask the question.
Yeah, hello.
Hello.
I wanted to ask, do you have products for freeform optic macro lenses for beam homogenizing applications, mostly laser beam homogenizer, to create a homogenized distribution?
That could be done. So if that would be something that you would be interested in, then I would say, then let's talk, because of course it has to do also a lot with your specific specifications. We do have solutions for these kinds of applications. So I would love to discuss further with you maybe after the talk.
Yeah, thank you.
Thank you very much. Okay, if you have other question, you can raise your hand through Zoom or ask your question in the chat as you just did, Happy. Okay, maybe it's too early for other question. We can continue and start the first session. We have are really pleased to welcome Bharath from STMicroelectronics. Bharath, are you here?
I am here. Thank you, Jeremy.
Yeah,
can you hear me well?
Nice to meet you, and it's late for you.
Pleasure. It's okay. It's late, but that's fine. This is the new world we live in. The COVID world is 24/7, right? Early morning, late night. It's okay. It's interesting.
True. So thanks a lot for participating.
Pleasure.
So you can share your screen and
wonderful.
Start
Wonderful, great. So thank you again for inviting me. Hello, everybody. Good morning to most of you. Hopefully, most of you in the morning. And that's good to be here. Thank you very much. Let me know once you can see this, Jeremy. Can you see this?
Yeah, you can see. Can you check the presentation mode?
Yeah, I'm going to go right there. You go.
Yeah.
Now can you see that?
Perfect.
Very good. Good. There's not a lot of time here. Sorry, let me go to previous. There's not that much time here, and a lot to cover. So I'll try to do the best I can, and try to do justice to the presentation, given the. I want to be very respectful of your time. So today I want to talk about laser beam scanning for augmented reality. It's a very high level, and I hope to get more questions, and we can always talk more afterwards. So my name is Bharath Rajagopalan. I am at STMicroelectronics, and I'm responsible for the company's overall strategic marketing, particularly AR, and I'm also chair of the Laser Alliance as well. Okay, so let me get right into it now. So let's talk about AR. Let's talk about what it means, where we are, and what the market looks like. We're going to, just give me 1 second. I want to close the window so I can see what I'm presenting here. Great. Okay, so this is a very interesting chart. And so what I want to talk about is really, there's sort of a dichotomy in the AR area. There is a lot of activity in what's called the smart glasses, which are really practical and useful devices, which allows you to have simple informatic display, and that is what we call practical and useful. On the other end of the spectrum, there is really a much more immersive and a niche application where it's much more complex and the rendering is much more intensive. And so what separates these two sort of use cases is, you know, on the one hand, you want to wear a pair of simple glasses like I'm wearing now, and you want to wear it all day long, 24/7 potentially. You want to be able to use inside and outside. And it has to be small, lightweight, and attractive in form factor. On the other hand, there's a whole suite of applications that are much more immersive and niche. What I mean by that is that you have very high resolution that's really goes towards the resolution of your eye. That has a very large field of view, so you can have much more interesting applications, much more immersive applications where you have rendering of very complicated objects, holographic rendering, world lock, spatial, very deep overlays, where you have very focal applications. So really, there's a very distinct separation of the market between those two devices. And we believe, a lot of us believe, that laser beam scan technology caters to display needs and the challenges of both markets. There's more to it than just display, but from a display point of view, LBS laser beam scanning is pretty well suited for both. So let me go a little bit more detail here in what this means. So when you think and look in terms of the type of devices that are required and the type of applications required, you can think about it in sort of very simple terms. On the x-axis, I show here a form factor from helmet-mounted, head-mounted displays, head-worn displays, all the way down to eyeglasses. And the y-axis, the levels of immersivity, from very simple informatic head-up display to full immersion, full interaction. And I haven't put the list of companies over here, but today in the marketplace, you have a range of devices from HMDs, which have a little bit more of immersivity, not full immersivity, all the way down to smart glasses, eyeglasses, which gives you just simple informatic head-up display. And everybody wants to go to up and to the right, as they call it. They want to go to full immersion, full interaction, yet in a small, lightweight pair of eyeglasses, so-called holy grail. We're not there yet. When will we get there? Hard to tell. I'm not going to prognosticate when that happens. So, anywhere from 2, 3, 4 years. But nonetheless, that's where you want to get to. But between here and there are gradations of immersivity, the gradations of size and weight and form factor that can be entertained in terms of delivering the AR experience that people require. So when you think about, okay, well, what does that really mean? This is great. It's interesting. What does that really mean in terms of practical use, in terms of the requirements for these kind of applications? So when you look at today, when you think about what's called smart glasses, informatic display, versus what people call XR, extended reality, or MR, mixed reality, these are some of the key parameters. Certainly, the use cases from a smart glass point of view is something you want to wear all day long. Because as an informatic display, you want to have information at your fingertips or in your eyeglasses for whatever you're doing and be able to get to it whenever you need it. Whereas in the case of a much more immersive application, much more compelling and a deep niche application, it's very, very task specific, whether you're doing medicine or whether you're doing architecture or those kind of very design intensive things. From an environmental point of view, having informatics when you're doing daily tasks, you want to be able to wear it indoor and outdoor. Whereas in the case of XR, MR, you want to be mostly indoors. And so that then leads to, well, where does the brightness need to be? If you want to be inside and outside, how bright do you need to be? If you're indoors, likewise, how bright do you need to be there as well? So what we've found is that in the case of indoor outdoor, you need to be much greater than 1,000 nits or candela per square meter, whereas when you're indoor basis, 500 is definitely more than enough. But there's some caveats here, and the caveat is the following: when you want to be in full sunlight and you want to see images in virtual images in a see-through pair of glasses in bright sunlight, I think most of us here on the call will know that 1,000 nits is it's not enough by far. It'd be much higher than that. So there's two ways to do that. One way to do that is to have much higher brightness. And if you do that, then you have to have a way of dimming it when you go in and out from bright to sun, from bright light to dim light, or indoor or to outdoor. Or you could have photochromic lenses for your glasses, which will then give you greater levels of a photochromaticity and therefore much more sunglass type, so that you can have much higher ambient contrast ratio. And from a form factor point of view, smart glasses, you want to be eyeglass style, you want to be lightweight, whereas for ARM or XR, for XR-MR, you can be a HoloLens type, which can be head-worn display. From a weight point of view, which is very, very important. If you're wearing something all day long, you need to be less than 80 grams. That's a spec for the eyeglass industry. Whereas when you're there for the XR-MR domain, you can be 200 grams plus or minus. And there's some caveats here. The key thing is that you can be heavier, but the distribution of weight around your head has to be designed so that the user does not have discomfort at all. Field of view is something that's not well understood at all. People say, I want more and more and more. I'll actually challenge that notion. I will say to you that for informatic display, we're showing 2D content, spatial overlay, informatics. You don't want to be more than 30, 40 degrees diagonal field of view. Any more, it's not usable for the user. Whereas if you're doing some very immersive application and doing very intensive rendering, you need to be much greater than 80 degrees. Ideally, you want to be 180, but that's very hard to get to today. So the greater the better for that application. Likewise, the resolution, since you're only showing smart glasses overlays and informatic, 720p is more than enough. However, when you get to, again, much more sophisticated holographic type of rendering, you want to be in excess of 1440p. In fact, you want to be probably even greater than 2K in that domain. Eye-box is very, very important. That's something people don't really think about, but you want to accommodate the interpupillary distance variation across a range of population, gender, age, ethnicity. And so what we found from studies that were done maybe 30, 40 years ago is that if you have a 10 millimeter by 10 millimeter eye box, you can cover greater than 90% of the interpupillary distance variation that you get across the human population. Power, very important for smart glasses. You want to be on the field. You want to have a long-term use. So you want to be less than 500 milliwatts. That's in the use case mode. Whereas for XRMR, you can be flexible within reason. What I mean by that is that if you're tethered, untethered, the size, the weight, and the use case allows you greater flexibility. And finally, latency is very important. By latency, I talk about motion to photon latency. For informatics, I think 60 millisecond, 60 hertz kind of a latency is more than enough. However, for much more sophisticated rendering, you need to be less than 4 milliseconds. So, and so when you think about the technologies that can deliver the kind of image quality and the size and the weight and the power, where we find laser beam scanning has the greatest potential in terms of field of view versus size and versus power. And so this chart, this illustrates basically, typically today you have LED or LCOS with or DLP that's very popular versus laser beam scanning is what we look at here. And we find is that from an overall size point of view, in terms of the total volume of the optical light engine, laser beam scanning gives you the best in terms of the size. And later on, I'll show you in terms of power as well. So when you think of AR and MR smart glasses, the holy grail and what people want to do is want to cram all the sophistication and complexity of Microsoft HoloLens into a pair of glasses, which is very difficult. It'll take some time. However, both form factors will need to have a compact form factor for display. These have very high and very efficient combiner optics. And as I said earlier, low latency, low power, and high brightness. So laser beam scanning satisfies all the critical requirements. A micro LED has potential. It is a future technology, but I think a lot of us know it's still very, very early in the development stages. It needs much more time to mature, particularly from a manufacturing point of view, and particularly for a full RGB. But even with the display, to do full AR MRXR needs more than that, at least a lot more sophisticated technologies in terms of SLAM, in terms of interactivity, in terms of a lot of the complexity that needs to come to bear. So for those of you who don't know, how does laser beam scanning work? It's very simple. You have a very small MEMS micro mirror. And over here, you'll see the picture of a photograph of a die next to a US 1-cent coin. And then in the package, this is the case of electromagnetically actuated micro mirror. And the way it works is basically you got a mirror. You've got 3 illumination sources, red, green, and blue laser diodes, as you all know very well. It's a very rapidly diverging beams. So you go through calming lenses to collimate the light. The light then gets combined, so it's collinear through going through some dichroic or beam splitter elements, hits the mirror. The mirror scans in both both in the X and Y directions in a raster scan basis to give rise to an image that goes to a screen or goes to your eye through a virtual image. And so over here, you can see a picture of what the size of the module looks like, both the electronics and the photonics, and that's designed to fit in a temple arm of a pair of glasses. To give an illustration over here, I will show you what this looks like. So in this illustration, you can see basically what happens here is you have RGB laser diodes going through calming lenses, hitting the dichroics, beam splitting, combining all the beams into one beam, and the beam then gets scanned by the MEMS micro mirrors and into a display or onto your eye through virtual images. So underlying technology is so how does it happen? So to make it happen from ST point of view, we develop what's called a MEMS scanner based chipsets. It basically consists of laser diodes, MEMS micro mirrors, micro mirror drivers, laser diode drivers, and some control algorithms to control everything in a closed loop way in order to give rise to a laser beam scanning system. And so today we have what's called a thin film PZT micro mirrors that's piezo actuated. In this case, we're using lead, zirconium titanate materials. Later on, we'll use more solid state, other materials as well. It is a 1280 by 720p mirror at a 65-degree optical field of view, and the range of brightness is anywhere from 1 to 1.5 lumens, 10 lumens, and the brightness will depend upon the losses you have in your waveguides. Certainly, a diffractive waveguide is very lossy. A reflective waveguide is very efficient. So depending on what the design looks like, it has a range of brightnesses that you could bring to bear for your system. So to put all this together, it takes a village. And so we realized that in order to create the market, we have to bring together optics, photonics, electronics, materials, substrates, a lot of ODMs, OEMs. And so we put together an alliance of companies. It's a nonprofit organization. We have founding members, regular members, associate members. And the goal is to develop the technology foundation, to develop the ecosystem so that our ODMs and OEM companies who are developing products then have access very readily for a range of technologies and products that they can then bring to market very quickly. So, display is important. It's critical, but it's a necessary but not sufficient condition. To have a fully functioning system, you have to have more than display and more than waveguide or combined optics. You need to have a way to look at head motion, look at where you're looking, look at the position estimation, to be able to communicate, to be able to listen. And so to do that, you need things like motion sensors and image sensors to be able to do some kind of pose estimation. You need to have ambient lights sensors to modulate the brightness. You'd have a microphone to communicate if you're doing maintenance, for example, or you're dictating notes, speakers to be able to talk and communicate to people, time of flight to do gesture potentially. So a lot of things have to come together beyond just a display. And on top of that, the interactivity has to be defined. The modality, how do you select the content? Do you tap, double tap, pinch, zoom, so on and so forth? So when I think of the system in general, we get caught up in displays a lot of times, but I want to tell you is that you need more than display. You need to have a lot of elements come together in order to give rise to for a compelling experience for the end user to use. So I just want to stop there because there's a lot of stuff to cover. We don't have a lot of time. I hope this is useful. It's a superficial analysis, superficial presentation, but I want to just give you a little flavor of the kind of things we're working on, what's required in the marketplace, not just as photonics and optics and electronics, but also all other aspects, so that this nascent market can mature and be able to deliver to the marketplace what it requires. Hope I didn't take too much time, and thank you for your attention. I'm happy to take any questions here.
Thank you very much, Bharath. Really interesting presentation. Thanks a lot for this. And yeah, we have a first question from Alper and Nadine. Please, Alper.
Hello, I have two questions. What is the lifetime of piezo actuators moving MEMS mirror? And as you shown in the previous slides, there are micro-optical elements such as beam splitter and collimating lens to collimate the light from RGB LEDs. And do you use waveguides or small micro-optical components there?
Great. So let me ask you, okay, I'll answer question in order. Thank you for your questions, and I appreciate that. So the lifetime of this is very long, right? And I won't get into details how many hours it is, but we basically go through typical reliability testing for consumer electronics products. So all our chips go through the standard, temperature humidity bias, drop test, vibration, high temp op life, so on and so forth, and they're all geared towards supporting consumer electronics lifetime. Now, in terms of the optics and stuff, so there's several optical elements here. So there's the waveguides, of course, after the light engine. And in the light engine, there are micro optics there as well. As you mentioned, small calming lenses, small dichroic elements. Those are pretty standard components, actually. They're not very exotic, but important. But for the waveguide, to answer your question, today we are using diffractively coupled waveguides because they allow for the best form factor. But we're also looking at non-diffractive types, such as direct retinal scan is one thing we're thinking about. We're also looking at reflective waveguides, both from using cascaded beam splitters as well as potentially using holographic optical reflectors as well. Did that answer your question?
Yes, thank you.
Great, wonderful.
Thank you for the question. Thanks, Bharath, for the answer. Do we have any other question? Okay, we have a question from Deep Agendas. Welcome.
Yes,
Dipanjan.
Bharath, it was a great presentation, and I'm very glad to join this. From ST, you have a lot of solutions for the future. So what do you think about, like, in near future, you show us a picture about all those features integrated to one smart glass. So what is the roadmap for this? Like, when we are coming with such devices?
Sure. We are working with the partners, and this is public knowledge already. So we are working with a lot of partners to develop products. Already today, there's devices out there today. This is public knowledge. Microsoft HoloLens uses laser beam scanning. Focus by North uses that. Others I can't speak about, obviously. So I really can't tell you when customers are going to deliver products, but we certainly think 2023 and beyond, you'll see increasingly more and more products that use laser beam scanning, as well as other technologies to boot. So technology is mature. We're in full production. We're qualified. It's really a question of when the marketplace can bring products to market. And so we hope and we estimate that starting in 2023 and beyond, you'll start to see increasing offering of products. But I'll also say to you another important fact, and this is really important, I want to say, is that there's a lot of hype around AR. We love AR, I love AR, I've been working for many, many years, but it's still a very new market. And so the biggest challenge for the industry, apart from desktop display, is the use cases. How do consumers use this? What will they do with it? How will they use it? How will they interact with it? And that has not been solved yet. And so the adoption into the consumer domain, which nobody knows what's going to happen, that'll be stimulated by answering that question. But we actually believe the use cases before that is to go towards enterprise industrial use cases for things like repair and maintenance, architectural engineering, construction, factory, warehousing, logistics. So you already see some products today. In 2023 and beyond, you'll see increasingly more products that are targeted towards those applications. Long answer. Hope to answer your question.
Yeah, that was a great answer. I'm expecting to see more coming in 2023. Thanks.
Me too. Me too. Thank you.
Thank you very much for the question. And we have another question from Eran Erkan from Morphotonics. Eran, if you want to ask a question by yourself.
Yeah. Hey, Bharath. How are you doing?
How are you?
Good. Thanks for the nice presentation. So I'm curious about your thoughts on micro LED based optical engines that are coming about. They're not fully there yet, but how do you see it in comparison to LBS, especially in terms of size, power consumption, but most importantly, enabling the market and opening it up?
Sure. I think micro LED has a great potential for the future, right? I think there's no question about it. I think as I'm sure you know very well, micro OLED has a lot of shortcomings, and micro LED actually addresses those. High brightness, certainly, great pixel pitch, good spectral characteristics, so on and so forth. I think micro LED is still many years away. Just a lot of challenges, of course, just to go from monochromatic to full color. How you do that? Are you going to do it monolithically, non-monolithically? You're going to do color conversion. I mean, as you may know, there's a whole range of things that have to be addressed there. And then there's the backplane solution, there's the integration solution, manufacturability. But micro LED, it will be here. It's a lot of investment. And how does it compare to LBS? I think they both coexist, because here's the thing. If you want higher and higher resolution, the size of the panel gets bigger. Micro LED is a fixed pixel display, meaning it's an array of pixels. So if you want to have greater resolution, you have to have more pixels. This is where laser beam scanning is interesting, because the scalability of resolution is much higher in terms of laser beam scanning versus micro LED for higher resolution. Just mean there are challenges, of course. So, for example, to get a high resolution in laser beam scanning, you'd have to go to a much higher scan rate or a different kind of architecture as opposed to size. And so that's where both, I think, coexist. So for certain applications, I think micro LED does really well. For other applications, I believe laser beam scan does really well. So over time, I do believe they'll coexist. And I think micro LED has great promise. But again, the question is, when will we overcome the challenges of color, the size, a pixel pitch, as well as packaging and the micro optics and so on and so forth. But all in all, I think micro LED has great potential, and I think that and other technologies coexist. I hope that answers your question, Erhan.
Yeah, thanks, Bharath.
Thank you very much, Jörg, for the question. And thanks again, Bharath, a lot for our presentation. It was really great to have you among us today. Thanks a lot.
Thank you so much, and I hope it's useful. Thank you for listening to me. I know we're very, very fast, but thank you for inviting me, and thank you all. This is 12:30 in the night here. I'm going to drop off and go to sleep, but thank you all very much, and please reach out to me if you want any other questions.
Thanks a lot, Bharath. Thanks again. Bye-bye.
Thank you, Jeremy. Good night, everybody. Bye.
So let's continue with a presentation from Mathijs Meulen from Morphotonics. So Jan, if you want to share your screen now.
Yes. Let me see.
Thank you.
Here it is.
Yes.
Thank you for giving this opportunity to show our work. It's really nice. My name is Mathijs Meulen of the company Morphotonics, and I would like to tell more about the use of roll-to-plate nano imprinting for high volume production of AR glasses. So within Morphotonics, we have developed a scalable nano imprint technology, and we believe this is needed to replicate the waveguides if the AR glasses is as successful as everybody hopes. So if it replaces at the end the mobile phone, then you need billions of waveguides, and then alternative replication methods will be needed. And to start with the conclusion, roll-to-plate nano imprinting, which is a scalable technology, which in one imprint pass can replicate hundreds of waveguides, might be the best or an interesting option. In this talk, I will show the results. But first, I would like to tell a little bit more about our company, a little bit. So Morphotonics is an OEM supplier. Our focus is on the supply of tools, roll-to-plate equipment. But we do not only develop the tools, specify the tools, we also develop the process, meaning that we also look at the materials. And the materials, which are the stem materials, but also the resin, are developed in our own clean rooms. These clean rooms are located in Veldhoven in the Netherlands, just next to Eindhoven. Our neighbor is ASML and Philips. And we have our own independent IP. I mentioned that we work on resins, on the flex stamp. We also work on the scaling. And so if you have one master, master is typically small, to end up replicating hundreds of waveguides in one imprint pass, you also need to scale up the master. And this is also a capability we have in our clean room, and which I will show. How does our technology look like? Well, as the name says, it's a roll-to-plate imprint technology. So we use a roll, and with the roll, we press a flex stamp. The flex stamp is the inverse texture onto the plate, the substrate. The flex stamp has anti-stick properties, so it will not adhere to the cured resin. The resin is applied in a coating method, it can be a dispense method, and having the flex stamp pressed into the resin, you immediately cure the resin and it solidifies, and then you can also directly delaminate the flex stamp. And the nice thing about our materials is that you can reuse the flex stamp hundreds of times. And we state above 500 times. It depends on the texture, and in commercial production, we have seen that this can be even over 1,000 times. We can replicate all kinds of structures, very small one, 50 nanometers, obviously the gratings of hundreds of nanometers, but we can also go up to hundreds of microns. And To do this, we develop our own resin, as mentioned, and also AR-specific resins. So we have developed together with Pixeligent, developed a 1.9 resin. And we have to develop these resins because our resins have one characteristics which is different from standard. Our resins are solvent-free. So they do not contain any solvent. That is potentially also one of the reasons why our flex stamp lifetime is long. So it has a lot of benefits. But you need to develop your own resins. We have a 1.6 resin without nanoparticles, already in higher refractive index, and then the 1.9 with a viscosity of 550 millipascals. We also have resins for etching or low refractive index for other applications, because we do not only look at augmented reality. Our roll-to-plate imprint technology can be used for many different applications, lighting, biosensors, 3D displays, and yeah, that is less interesting for now. But the good news is that while AR could be will be coming in the coming years, we already have our tools in the market making commercial products. So it's a proven technology, making already, for instance, 3D displays, which can be bought in the USA. How does it work? Yeah, and here I think the really the benefit for augmented reality comes. So for all applications, but especially for the AR market, mastering is tedious. It's complex. You would like to have maybe a slanted grating, blaze gratings, all kind of different gratings, and this makes the master expensive and time-consuming. And typically, you make one waveguide on the master. You can replicate it, but if you replicate each time one waveguide, you will never end up serving the complete AR market. So what do? We replicate in multiple steps. We ensure that we have a scaled-up master having, for instance, 25, 30 waveguides. And moreover, we can ensure that we have multiple of these scaled-up masters on one flex stamp. So then you cannot replicate the multiple of the 30 waveguides on one product, on one wafer, but you can replicate them on multiple wafers. So we, with our larger area imprint tools, which can replicate on sizes of 1 square meter or even larger, then you can replicate 9 wafers at the same moment. So you can put 9 wafers together in one tool, and then on each wafer you can replicate 30 waveguides. Yeah, and then you end up in the case that you can make hundreds of waveguides every 5 minutes, coming to millions, tens of millions of waveguides in a year. And we believe that this is the solution to serve the high volume consumer market. You might notice that here we show that we replicate on squared wafers. We demonstrated that. I will show you the result. We worked on this topic together with the company Schott, supplying squared wafers, which are available. It's very interesting because then you have 25% increase of imprint area. Obviously, we can also replicate on round wafers or larger wafers. So how does it look in practice? And we reduced it to practice with a nice group of companies. We did not did this all by ourselves. So we worked with the company Light Trends to design the waveguides, nailed to master the waveguide, a Schott to supply the glass, and Optic fidelity to measure the results. So we started with one master supplied by Niels. We made the 30 of submaster, and we ended up making 4 submaster replications on 4 waveguides supplied by shot, having 120 waveguides in one imprint cycle, which can be further scaled up to above 200. The replication was on 1.9 glass, a squared 1.9 glass with a 1.9 resin head supplied by Xcelligent. And then the question obviously is, this looks nice, but what is the quality? So we asked Optifidelity to measure the quality. And they looked at the grading period accuracy, which is the lower results. And then they showed that we have a period accuracy below 20 picometer, or even below 10 picometer for the expander. So this is on par. These are good results. Another topic, or a correlated topic, is obviously the dimensional stability. Is every texture located on the right spot? It does not, like you show with the period grading, you can also look at on a more large area scale. And this is what we showed in the upper graph. If you with the masses, we can see how much stretch we have on a larger scale, and then our stretch of our complete system, including our flexible stem, is below 5 micron. Typically, it's below 2 micron on Gen 3 scale. And this sounds straightforward. We have to apply special flex stem design. So we developed a flex stem design especially for augmented reality, which we call it dimensional stable. It has a temperature expansion coefficient of below 5 ppm. Most important is that the waveguide works well. It was a simple waveguide designed for green light with green LEDs, but it functions well. And so already within the first trials, we made functioning waveguides, which is an interesting and a good result. We do this with our large area imprint tools. I would like to tell a little bit more about it. We have two systems, the Porter system as well as the Aurora system. The Porter system, then everything, all handling is manual. We have smaller system where the roller has a width of 600 millimeter. We have also a larger system, the Porter Snell 1100, where the width of the roller is 1100 millimeter, and then you can replicate on Gen 5 size, 1.1 meter, 1100 meter by 1300 millimeter. Thickness of the glass can vary. We can handle directly 0.5 millimeter, but you can go even thinner if you use a carrier. And then you can do this all inline, fully automated using an Aurora line. And then you can think of having an imprint with a takt time of every 2 minutes. Every 2 minutes, an imprinted plate comes out of the line. And we believe that this is the route forward to serve the AR market. And this is also the last slide. So we develop all the work with a very nice and enthusiastic team. I'd like to thank the team, but also thank Fabulous and the Epic Consortium for all the nice work and support.
Thank you very much, and thanks a lot for your interesting presentation. So I would like to ask if we have some questions in the room. So yes, we have a question from Pavel. Pavel from Huawei Technologies, please.
Hi, Jan. Thank you for a very interesting presentation. I have a question about, you mentioned substrate size. The question is, how big can be in fabrication single waveguides? Can you fabricate, for example, outcoupling waveguides with size like 300 millimeter by 200?
Yeah, that is possible. as you know, the best results or the best waveguides are made using a high refractive index glass, and then you have the largest field of view. But the high refractive index glass is at this moment not yet available at Gen 5 size, and it will take quite some years to have it available at these sizes. But then it does not mean that our technology cannot be used. So we do not have to replicate on only large areas. So these Gen 5 sizes. We can add multiple plates together, smaller plates as you see here, and replicate on multiple wafers in one pass. And this is our proposal. And that can be squared wafers, like shot developed, squared 1.9 glass, but it can also be round wafers.
Like in your slides with master 1, if it's size like 400 millimeter by 200 millimeter, you.
Yeah, indeed. So if it is in 300 millimeter round master, and you have just a one up, but then typically the master will not be that large, but or the master has already a multiple waveguide or contain multiple waveguides, then we can directly replicate it again on 300 millimeter wafers or on 200 millimeter wafers. Yeah, and then having an intermediate upscaling step, and you can optimize the number of waveguides on the imprinted wafer.
Maybe one question more, because for outcoupling region for waveguides, we need some non-uniformity in grading, and can be it's implemented in your company, or it should be already in master, like different fill fraction for grading or different depths, it should be in master, or after nano-imprinting you can make non-uniformity by etching, or can we do like non-uniform?
Yeah, that's an interesting question. But with our replication technology, the nano imprint replication, but I also think it's the same for other nano imprint technologies. We really replicate the master. So if the master has a certain roughness, we will replicate it. If it has a certain depth, we will replicate it. And we cannot steer and alter the depth. So these waveguides, which you see here, had, for instance, a varying track pitch and a varying grating height. So, and yes, we replicate it, and we replicate it correctly. But we cannot, in our technology, we cannot start with a uniform master and making it having a certain step height over the waveguide. It is possible that nano imprinting is used as an etch mask. So, so it can be used in combination with etching, and then depending on the etching method, maybe if it is an ion beam, then indeed you can vary again the depth locally.
Question: do you have etching process in company to transfer mask to glass?
Could you repeat the question?
Do you have this etching process in company to transfer polymer mask in glass?
We do not have etching tools, but we have different projects where we worked with other companies on this topic. And at the latest SID, we have given a talk on this topic. So Pim Veldhuizen, my colleague, he showed that together, for instance, with the Holst University, we could make TFTs, working TFTs, using nano imprinting as an etching mask.
Thank you very much.
Thank you for your question. And we have just time for a short question from Alperin Edin, please.
Thank you for the great presentation. My question is related to flexible stamps. Do you have a strategy to use laser-driven translation for flexible stamp by using UV light?
Yeah, we use so in our roll-to-tape process, obviously there's a UV tuning step, so we use UV LEDs not laser, but well, standard available UV LED single wavelength. At the moment, there are no other complex lighting steps involved. I can think of a few, but that would make the imprint process maybe a little bit too complex.
Okay, thanks.
Thank you very much, Harp. Thanks a lot, Jan, again for your presentation. It was really interesting. So if you have other questions for Jan, maybe you can stay after this morning and discuss during our session, the talking session. So let's move on with Ruben Mohedano from LIMBAK. Ruben, are you here?
Yeah, I'm here.
Yeah, hi, Ruben. So you can start to share your presentation then.
Yeah, hold on a second. Apparently I have to I'm having problems because I'm not using my computer. I'm having problems sharing my screen because I have to. I don't have permission to. So maybe, I wonder, can I send? Let me
maybe check this with Elisanda, Ruben.
Yeah,
and we can you can pass.
You can go.
I can share the screen if you send me the presentation. Sure.
Yeah, that's what we're going to do. Maybe you can proceed with the next speaker.
Yeah,
and I'm going to take care with Elisanda about this. Okay?
Yeah. Check it with Elisanda. So now, Guillaume, are you here? Guillaume Tison from Imagine Optics.
Hello.
Hello, Guillaume.
Yeah.
So you can start.
Okay, I'll share my screen right now.
Yeah.
Okay, can you see my screen?
Not yet. I can't see it on my side.
And now?
No. Now it's okay. Now it's okay.
It's okay?
You can start. Yeah. Thank you.
Okay. Thank you. So thank you, everyone. Have a nice day. My name is Guillaume Tison, and I'm going to speak on behalf of Imagine Optic. Imagine Optic is mainly known for four kinds of application: XUV imaging, bioimaging, hyper laser, adaptive optics, and optical metrology. And today I will focus on optical metrology, especially for AR and VR and freeform applications. So I'll start with a quick introduction of the company. We are now 25 years old, about 50 employees, mostly in France, but with some distributors in Asia and the US. We have been selling waveform sensors for quite a lot of time now, with more than 1,000 sensors all over the world. And we're also part of a few consortiums like EPIC, for example. As far as we go with optical metrology, we have quite a lot of experience with many industrial partners that you may recognize some logo. And in the last few years, we had several interaction with people from the ARVR community. We can feel that there's some growth here. More and more interaction with this kind of applications. So let's have a quick look into our products. There's a new thing here. We call it the OEC family, like the Optical Engineer Companion. It's meant to be like the Swiss Army knife for the optical engineer in its R&D laboratory. So you've got some building blocks and many accessories that you can just add together. It's very modular. Everything is compatible with each other, and you can basically build your own system up to what you need, up to 6 inches in diameters, for example, for the very large aperture airflex systems. And it has all the advantages and inconveniences of the Shakatman technology. Now with a quite high resolution accuracy, a rather large dynamic range compared to other waveform sensing technologies. It's also vibration sensitive, compact, and well, I find it easy to use, but I agree that it's kind of subjective. So just now I'm going to introduce, this is a spoiler, this is not commercially available yet, it's going to be available next year. For now, it's currently being tested by some of our close partners, but there's a new thing coming, which is called the Meso, and it's specialized for the measurement of thin parallel optics. So it can be mirrors, beam splitters, window, searchlight, wafers, and everything that's basically that has little to no optical power. The innovation here is that this device is undisturbed by reflection from the back surface of the sample. In fact, it's able to measure both surfaces with only one manipulation. So this is quite new, and I'm sure you'll be interested to see this product going live at the next Photonics, I believe, next year. Okay, so now I'm going to introduce you 4 case studies which are relevant to the topic of today about AR and VR and freeforms. So the first one I wanted to speak about is the testing of a windshield, which was embedded with thin film. Thin film embedded into components is quite trendy in some design for augmented reality systems, because you can just add some polarization manipulation, polarization function to your components. So we did it with the Airflex system. So everything starts with the Shakatman waveform sensor, upon which we had a source in a conjugated fashion, and then we had a module with the correct numerical aperture, and then a large afocal system to increase the diameter of the component we want to measure, and then we can measure it either in reflection or in transmission, and this allows us to have a look into the aberration that's brought by the thin film, which is embedded in the windshield. So here you've got a picture of a stitched reflected waveform from such a windshield. So this is not very micro optics like, but it's kind of into the topic still. Now with a similar Airflex system, but without a large afocal component, we were able to measure microstructure molds. So this gets into the micro optics subject right now. And in this example, we had milli optics, not micro optics. The diameter of each sub element was about 1 millimeter in diameter. And similarly, we were able to stitch together a large amount of sub images in order to quantify the optical power map of the whole component, which was a mold. So since we're speaking about microstructures, let's speak about microlenses and Shakatman technology. So our sensors basically are made of a microlens array, which is in front of a camera sensor. And so the microlens array quality is critical to our own product quality. So we measure them with our own products. It's like a snake eating its own tail. But here you can have a look at a phase map of one of the microlens array of our product. So here the micro optical element is about 80 micrometer in width, and so it's an array. So we are able to isolate micro optical components in order to quantify their quality, their aberration, and of course by doing it randomly over a surface to assess the repeatability of the manufacturer of the manufactured product. Next, the first application is more focused on freeform. Courtesy from the Onera, we had some phase masks that we could measure. And here, for example, we used the Hazelsphere, which was at 1.55 micrometer wavelength. and the phase map is 28 points in the diameter, and the phase indicators are 2.45 micrometer PV. So this is wavefront indicators, and we measure them with very, very similar product, but with a new thing. This is the lift innovation. Fun fact, the lift innovation is based on a paper which was published by Onera researchers too. So it's, thank you, Onera. Credits go to you. Now, so basically this is almost the same hardware. The micro lens are slightly different in order to allow us to achieve this lifting of the phase map, and same component, almost the same wavefront sensors, but 4 times more resolution in each direction. So as you can see, both phase maps look very close to each other. The RMS indicator of the phase map are in good agreement, and just for the purpose of proving that this lift innovation is keeping up with the quality of the wavefront measurement, we measured the similar, exactly the same component with another wavefront sensor, which has smaller microlenses. So basically, this tends to prove that the lift technology is purely allowing us to gain in terms of resolution. So there is a drawback here, which is the calculation speed. It's hard to go above the Hertz with the lift technology because it's quite expensive in the calculation process. So that's it for me. I might have been rushing a little here. Thank you for your attention. We are happy to provide more information, be it on meso or the lift technology. If you are interested, I've got some slides next if you start some technical questions about that. And I must say that we are quite happy to perform tests on your samples to help the community to grow together.
Thank you very much, Guillaume. Thanks a lot for our presentation. And we all know that how much metrology is important for micro-optics. So I'm going to ask if we have some questions for Guillaume from the participant here. Okay, maybe I can ask you a question. I would like to know if you were able to integrate your systems in mass production on production line, for example. It's possible with your system?
Yes. So basically, all these products, all these are modular and can be customized to really fit a specific application. So yes, we do have experience with the very specific application in production, where we just select the best optical configuration and fix it and simplify the software for technicians or automatization. So there are quite a lot of we have quite a lot of experience with industrial partners just to customize our solutions for their specific needs. Indeed.
Okay. Interesting.
Our software comes with a SDK, so our clients are able to build their own application.
Okay.
To emphasize what's really important to them. I just maybe I just for a few seconds. I just want to go back to the lift slide. This new technology is already available, and it is not purely achromatic. Our technology is completely achromatic, but the lift innovation is actually software based, where the wavelength is a parameter. So it's wavelength dependent in the sense that the user needs to pay attention to the wavelength of its system. But so in essence, it stays achromatic, but you need to input the correct wavelength. That's it.
Okay. And are you already involved in micro-optics metrology project?
Sorry?
Are you already involved in micro-optics metrology project? I mean,
not that much, in fact. Most of the micro elements we measured, we do have one being industrial partner where micro-optics are currently being discussed. Micro-optics metrology is being discussed, but not for long. But we are expecting more and more of such applications. For now, it's mostly a tool for us to measure the quality of our own micro-optics. But if anyone is interested, I mean, we are not limited by just spherical forms. As you can see on this slide, we can also do freeform micro-optics.
Okay, very interesting. Thank you again, Guillaume. Thanks a lot for our presentation. If you have some question for Guillaume, please you can contact me or you can contact him directly in the chat. Thanks a lot, Guillaume. So let's move on with our next speakers. Jörg Reitterer from TriLite. I would like to ask you to, we have Ruben. Ruben, you are here again. Okay, let's move on. Jörg Reitterer, can you try to share your screen and start your presentation from TriLite?
Yes, more than happy to do that. Thank you. Let me quickly share the screen here. I hope that you can see my slides now. Let me switch.
Yeah, that's great.
Okay, perfect. Okay, so thank you very much for inviting me to give this talk here in this workshop. So I'm Jörg, I'm CTO here at TriLite and one of the co-founders of the company. And here at TriLite, we are building so-called laser beam scanners for high volume consumer augmented reality applications. And let me quickly start with our vision. And the vision we have is that everyone enjoys augmented vision as lightweight as the eyewear of today. And for us, this includes a couple of very important points. So first of all, we are focusing primarily on augmented reality applications with all the products we are developing. And also when it comes to technical requirements, we are clearly focusing on consumer requirements. So as you can imagine, augmented reality glasses, and as was also mentioned in the first talk today by Bharath from ST, size, weight, and other characteristics like brightness, etc. They are very, very crucial to be accepted by end consumers as a device that you would wear all day long. And image quality and power consumption and others are also very, very critical to all of our clients. So when we design our products, we have a very clear focus on the consumer side of the applications. And also this is very important for us that we need to use, first of all, components in our system and also use assembly processes that are scalable for very large volumes, talking about millions and tens of millions of devices per year. So everything that we develop has also this mass manufacturing aspect in mind. Here is a very quick overview of some of our history. So we founded the company over a decade ago. And since then, we have been building laser beam scanning systems in many different shapes and forms, all leading up to, let me quickly turn on my pointer here, all leading up to the latest generation, so-called Trixel 3 laser beam scanner, which is designed from the ground up for augmented reality applications with certain waveguide combiners in mind. And also, again, the mass manufacturing aspect when designing this product is key to us. So now let me quickly introduce you to some display architectures that are used in augmented reality systems today. The first two categories here are all so-called panel-based displays. And at the very bottom, you can see, for example, liquid crystal on silicon and digital micromirror devices, which are reflective panel-based displays, meaning that you have a panel. It's an array of pixels in a kind of 2D arrangement, and you need to illuminate this panel with external light sources, typically some LEDs. So you need illumination optics, polarization beam splitters, you need projection optics. So all in all, everything is very big and bulky, as you can see in this schematic view here. This top part here is basically the display engine, which is then used to couple light into a combiner optic, which, for example, could be a so-called waveguide combiner. And the second category of devices with micro LED and micro OLED displays is already much more compact, as you can see, because it's self-emissive, so you can get rid of all these illumination optics. But you still need those projection optics, and you still have a 2D array of pixels. It's a panel-based display, and as already mentioned by others before today, there's a certain limit how small such a pixel can get. And once you want to increase resolution, you want to have full RGB systems, you want to increase the field of view of the system, those type of devices tend to grow in size and not get smaller, and which is exactly what you need to avoid for consumer applications. And this is exactly where the laser beam scanning technology is different. So it's not a panel-based display, but it's rather a scanning-based display. So you are using an RGB laser module. You have a scanning micro mirror, a so-called MEMS mirror, and in some architectures, you also are using some so-called relay optics to couple the light from this laser beam scanner into the waveguide. Our systems, on the other hand, are not using any of those relay optics, and we are also using just a single 2D MEMS mirror, because in our opinion, this is the way forward, how to make this the most compact way you can. We are using something called a direct coupling approach, where we scan the laser beams directly into this input coupler of the waveguide, which is then via the waveguide relaying the image to the eye of the viewer. So this is on a system level giving us the smallest, lightest, and also brightest display engine, because with this laser diodes that we're using, we can get to very high brightness levels, which is something that other display technologies are struggling a bit with. Here you can see a schematic of this direct coupling. So we have this Trixel 3 laser beam scanning engine here. We are directly coupling into this waveguide device, as you can see here. And this is giving a very, very compact form factor, where this laser beam scanner can be directly integrated into the temple of your glasses, for example. We at TriLite, we are also designing and manufacturing our own RGB laser modules with some optical components in there. As also mentioned by others before, there's some collimation optics you need, some ways how to shape the laser beam, some way how to deliver it to the MEMS mirror. So all of this design we are doing in-house here, and the manufacturing we are also doing with our manufacturing service platform. We are also using 2D MEMS mirrors, and last year we announced that we are partnering here with Infineon, which is one of the leading MEMS companies for large volume applications. And all of our devices here that we produce are optimized for so-called waveguide combiners with this direct coupling. We can also work with holographic combiners, also called this direct retinal scanning displays, because the laser beam scanners inherently are also compatible to that kind of architectures. Here you can see some of the key specifications. So we are aiming at something like less than 1 cubic centimeter for the total volume. Some other key specifications are the weight. It's very crucial for consumer devices as well. So we have 1.5 grams here for the total LBS system. And also what's important is the brightness. So we can get something around 15 lumens out of the LBS engine, with some brightness out of the waveguide, for example, giving you something like 3000 nits, which is fully daylight compatible. Power consumption is also very important, and we are aiming for the mass production version of that laser beam scanner for a value of 420 milliwatts for the total system. This includes all the drivers for the lasers, for the MEMS mirror, all the image controller, the lasers themselves, the MEMS mirror themselves. So basically the full system that you need to display RGB images. Something that we put a lot of emphasis on when designing our systems is that we want to shift complexity from the hardware to the software domain. And when you have such a laser beam scanner, the nice thing is you are not fixed to a kind of pixel grid. So you're scanning laser beams, and by timing laser pulses correctly, you can do a lot of very interesting things in software. So one of that is, for example, that you can get rid of any kind of image distortions in the system. You can overlap RGB channels perfectly without using RGB combiners. And this is something we are fully leveraging in all of our systems. And also very importantly, this enables us to design certain optomechanical architectures that are simplified in terms of the process flows when we assemble the system. So we can also use this software approach to simplify not only the components, but also the assembly, to loosen up tolerances, to get to higher yield when assembling large volumes, etc. So this is why we put a lot of effort into the software domain when we design our systems. As mentioned before, manufacturing is very important to us. So we have set up this so-called TriLite manufacturing services platform. So we are working with high volume contract manufacturers for assembling all of those parts. And we are sourcing certain components from strategic suppliers. Let's say, for example, the MEMS mirrors mentioned before. Also optical components like lenses and others. The RGB lasers also from the electronic side. We have a laser driver in the system, a MEMS driver, etc. And also some image controller, power management, etc. So all of this is basically adding up to the full LBS system that we are then using our contract manufacturers for to assemble everything really from the laser level up to the full system, including all the calibration that is necessary to give you the best possible image quality. So to summarize, we are clearly focusing on high volume applications with our laser beam scanning systems. So this is also with respect to the technical specifications like size, weight, image quality, brightness, and so on. We put a lot of emphasis on software versus hardware in the system design. And we are right now in the process of running towards production, and we are planning to ramp up our 2D LBS for augmented reality next year. And we are aiming to be the first 2D LBS for augmented reality in high volume production with that product. Okay, so thank you very much, and I'm open to any questions from you.
Thank you very much, Jörg. Thanks a lot. So we have, okay, first question from Deep Agendas, please.
Yeah, Jörg, it was a great presentation. And I would like to ask that how this LBS system is competitive to micro LED projectors. We have from Jadebird Display, these micro LEDs offerings. So what do you think is the could be nice to look into the LBS on one side and micro LEDs on the other side? So what do you think could be more suggestible option according to the technology we are moving ahead?
Okay, thank you very much for the question. It's a very important question, and we get this question a lot. And as mentioned before, just on a very basic level, all of those panel-based display, doesn't even matter if it's micro LED, micro OLED, or any other panel-based display, it does not scale very well towards larger field of view, larger resolution systems. When we talk about micro LED in particular, one very big challenge is that many applications and many of our clients want or need to have RGB systems. So it's a single color solution is not viable from many of our clients at least. And for micro LEDs, this is a very big challenge right now in terms of the manufacturing processes to get a single panel RGB solution. What others are doing, and you were mentioning, for example, Jadebird, is that you can use 3 separate panels, one for each color, and you can combine the image, etc. But this again is not a very compact solution because you lose a lot of image quality, and it's not compact because you need additional optical components for combining those 3 colors basically. Another very big topic is always brightness. So with micro LEDs, while some of the colors are somewhat efficient, some others like red, for example, right now are not very efficient. And when you build an RGB system, you always need to balance the colors to give you a nice white balance, right? So you need to have a certain ratio in terms of the brightness levels. And if one color is lacking in terms of efficiency, it reduces the overall brightness substantially. So this is also where we see very big advantages for laser beam scanning because you can get, let's say, 15 lumens out of the projector, and you can go even beyond that. But this is what we see as a very nice spot for the augmented reality applications. But with full RGB micro LED solutions, it's very tough to get to that point. I'm fully convinced there will be a certain split in the market at a certain point once micro LEDs have matured. But for the time being, laser beam scanning can be quicker to the market compared to full RGB micro LED solutions, at least in our opinion.
Yeah, that was a great answer. Thanks.
Thanks a lot for your question, Stanjan. Thanks, Jörg, for your answer. And I would like to ask you, Jörg, how Fabulous could support you with your maybe technological issues or something like that? How?
So thank you for the question. And as mentioned, we build a system where we are using lasers. We use some collimation optics, some additional optics for shaping beams, delivering beams to the MEMS mirror to be scanned. So in many different areas, I would say in such a system, one could use freeform micro lenses. And in general, freeform micro lenses have advantages when it comes to certain design opportunities you have. You can get, let's say, an improved beam quality. And you can also use freeform micro lenses to shape the beam in very unique ways. And this is all something that we are exploring for future product generations. And when talking about Fabulous, I think, at least from our point of view, the very big advantage is that Fabulous is supporting from the design to the prototyping to the pilot line up to volume production, which is something that for us, since we want to target high volume consumer applications, is also very critical.
Great, thank you very much, Jörg. Thanks a lot for your presentation again. Very interesting. Thank you.
Thank you very much.
So let's move on. Ruben, are you ready for your presentation?
Yeah.
Okay.
Yeah, let me try.
Yeah, please.
Hey, can you see my screen now?
Yeah, can you try the presentation mode? Perfect, that's good.
Okay, thank you. So never go live with a computer you are borrowing. This was a problem of not having permission to share my screen. The computer is not mine, so they had to make me, give me some credentials. So anyway, this is what I'm going to present today. Thank you for being there. I'm going to talk about freeform mini lens array optics for mixed reality on behalf of the team I work with in LIMBAK. 3 parts in the presentation: an introduction, a brief description of what's going on with optics having up to 4 channels, and then we will go to the mini lens arrays, so N channels. So basically in VR, most solutions are based on rotational asymmetric lenses. The goal here is producing an experience which is very immersive. So you have to present the information on the display so that the user perceives a very large image surrounding him. So he feels immersed in this virtual world. That's why the field of view of the information has to be wide, beyond 90 degrees probably. We also typically compare different systems in terms of efficiency. So light coming from the display eventually hitting the pupil and the retina eventually. And also it's important to get to know the angular resolution in pixels per degree because the image quality and the experience depends a lot on that. And also we compare systems in terms of depth. So if the depth of the system is large, that means the size of the system is also large. So by using rotational asymmetric lenses, if you want to achieve the PPD and the field of view, the display will have to be located very far from the lens and far from the eye. And that produces headsets which are, as you can see in this drawing, very large and bulky, and those are the headsets that are currently populating the market. There are other options. The most common one to reduce the size of the system is called the pancake lens. It's a solution based on light folding. This system has the ability to fold the light and reduce the optical path length from the display to the eye, but it does it using polarized light, reflective polarizers, and a half mirror. Because of the half mirror, only 14% of the light eventually hits the retina. That means the efficiency of the system is very low and makes this system potentially incompatible with a standalone system, which is eventually what every brand wants to achieve in the future. Nobody wants tethered solutions. So this system works very well in reducing the depth of the system, but as I say, the efficiency is very low. There are a couple of solutions based on pancakes, more to come probably in the next year. These two have been commercialized by Huawei in Asia and 3M and Pegatron. So there is another way to reduce the size of the system down to size of sunglasses without giving up the efficiency, which is the major drawback of the pancake, and it's going to multi-channel optic. This has been there like for some time now, and it is inspired on the, if you want, in the eyes of insects, which have several optical channels and process the light in parallel. This way, as I will show later, we can reduce the focal length of the systems and get the system size reduced a lot without giving up the efficiency. So light transmission can be kept high. So let's see first the solution based on a couple of channels or 4 channels. We at LIMBAK have patented a solution called the Clover, which is a 4-channel optic that is able to locate the display very close to the optic and do light folding by, refracting the light, reflecting in a mirror, and also reflecting by total internal reflection in a very compact folded optical path that eventually produces a system that is very close to the eye and is able to achieve the field of view that is required in VR to produce the feeling of immersion. You can compare the system, the conventional system on top and ours at the bottom. So the total track length distance from display to pupil is reduced more than down to a half. So this eventually will allow the headsets to reduce a lot in size. If you compare the Clover with regards to conventional solution in this diamond drawing, you can see that the resolution and field of view is kept in the same levels as a conventional system, and the depth is reduced down to a half. Without giving up a lot of efficiency, the efficiency is reduced, but only a little because of the use of mirrors who have a limited reflectivity. And yes, the Clover, because of using these 4 channels, you will have to display the image on the panels split into 4. You can see that there are some areas in which there is some redundancy. So some pixels are repeated over the different channels because for certain directions, when the pupil moves around the system, a given direction is seen through adjacent channels. That means the pixels have to be repeated in some areas. So this implies a reduction in the resolution when you go to more than 1 channel. This is how the optics work. You can see this in this video, that there are 4 images in the display, but when you see through the lens, the image stitch perfectly on your retina, and you don't notice there are 4 images and 4 channels in the optics. They all merge together and you feel one single image. So you can go and keep splitting your optics and exploding the optics into more channels. The more channels you use, the more you reduce the focal length of the system, the more you can put the display closer to the eye, and eventually you can achieve a system which is the size of sunglasses. So we have this technology called Trenza with lots of mini lenses together, which is able to produce a decent or a good resolution of 30 pixels per degree. The efficiency is very high because it's just refractions, and the depth can be reduced down to only 8 millimeters, so like a sunglass, and produce a field of view of 100 degrees. This also depends on the display pixels per inch, but there's a path to achieve that goal. And you might be wondering, how is it possible that when you are using more lenses and you have this redundancy issue and the necessity of duplicate pixels in the different channels, how can you produce that kind of pixels per degree? So that angular resolution. The key is based on a few things. And the first thing is that every channel in the TriLite approach is a freeform. It's not rotationally symmetric. That gives us degrees of freedom to have more resolution and in the field of view that we want. The other is what we call passive foveal super resolution, which is basically a technique based on two things that lean on how the human eye really works. So we take into account a very special feature of the human eye, which is the human eye is very picky in the gazing direction. It can achieve a very high resolution in only ±3 degrees around the pupil direction, but it perceives everything very blurry beyond that. So we are going to use that in our designs optimization, and we are also going to produce a very strong and variable magnification to use more pixels in the directions where the pupil is actually going to gaze. And we forget about the directions that are not directly gazeable. And the most beautiful things of TriLite is interlacing. Okay, this is another technique in our patents that is going to help us improving the apparent resolution of this multi-channel device. So interlacing is a concept that is based on dividing the mini lens array into different clusters. So we know every cluster lens is going to project a set of pixels through the pupil into our retina. And we design different clusters so the pixels are projected interlaced with the cluster adjacent to this. By doing that, we are able to, adjacent clusters project pixel images that interlace with each other, eventually producing a rise in the apparent resolution. So this is what we call interlacing. And we do this for all the pixels in the display and for all the colors. So this holds for red pixels, for blue pixels. Eventually, we can produce images where the resolution is increased. Okay, so back in 2019, we were able to prove this concept with an off-the-shelf array. It was not a freeform array. It was off-the-shelf, and by using this mini lens array and a display which was biased and directed the way we wanted to do the interlacing, and we produced the set of images that were required to demonstrate interlacing, we were able to increase the apparent resolution of the device from 5 pixels per degree to 17.5 pixels per degree. This device is a proof of concept with limited eye box, and as I said, is an off-the-shelf MLA. Thanks to Fabulous, we are now working on a freeform mini lens array, able to achieve a much better performance, up to 26 ppd we expect if everything is manufactured according to our specs, and a field of view of 80 degrees. We are manufacturing this with the partners at Fabulous. UPMT is taking care of the origination, so it's making the molds. STMicroelectronics is making the imprints, the replications using wafer level optics, and they are doing a great job. In a first attempt, we wanted to collect some information about how the imprints are close to the master, because there are shrinkage and other things that we need to take care of. And we are in Fabulous, and this is an example of how Fabulous can be producing results beyond what anyone else can do in the market. In Fabulous, we are able to manufacture a first sample, measure it, see how close to the design is, and work on a compensation of the mold that eventually will help us in compensating shrinkage. So this close collaboration of originators, replicators, and optical designers will make us very strong. So in 2023, we expect to have this demo manufactured within Fabulous, able to demonstrate 26 pixels per degree, 80 degrees field of view, 8 millimeters thickness. And in 2024, if we are able to work on the display and have a custom display, another type of optics, doing some eye tracking and myopia correction, we can improve the system a lot. So this is how the 2019 prototype looks like. This is how the 30 ppds Trentha product in 2024 might look like. And yes, the conclusion is multi-channel optics is the path to achieve a very compact, reduced size system in VR and MR without giving up the efficiency. So these will be compatible with standalone devices, which is the future. And freeform surfaces are necessary for best image quality. If we are able to, on top of that, have some impact or some decisions about the display subpixel structure, and also doing pupil tracking, we can get a hell of a system using Trentha. So that was all. Thanks to Fabulous, especially for supporting our work with Trentha, and to all the partners in Fabulous for believing in this and helping us to make a prototype to demonstrate it. We hope we succeed.
Thank you very much, Ruben, for the presentation. It's really nice to see how Fabulous supported you in this way for VR market. So I would like to ask to the participants if we have some question for Ruben. Maybe I can ask just one question for you, Ruben. So you are already involved in the VR market. Are you working with integrators for this technology already?
We are obviously the customers that we have are not are confidential.
Yeah, for sure.
But yeah, the brands that are in the market are evident, and some of them are customers of ours. The only brand that I can disclose is already known by many of you is Lynx in France. Lynx is using the Clover in their optical system, and we hope they can reach a market very soon. And regarding other technologies, as I say, I cannot disclose them, but yes, we are connected to many important brands.
Great, very interesting. Thanks a lot, Ruben, for this presentation. Maybe we can move on. We're a little bit late, but that's okay. Thanks again, Ruben, for the presentation. And I would like to welcome Yuka Perento from Incron. Yuka, are you here?
Yes, I'm here.
Perfect.
Just share my presentation here. So you see my presentation?
Yes, you can start. Okay. Thank you.
Oops. Okay, so basically what I would like to discuss today is the Incron's approach, which we have changed a little bit. Like at the core, we are the materials company, but we are now also coming a little bit to the process side. But let me try to explain it to all of you. So first, short background. So Incron is founded in Finland 2013, and then later, 4 years later, we became a group company of a Japanese stock-listed company called Nagase. And through Nagase, we have a global presence. I don't even show all the locations they have here on the map, but basically its continent is covered by Naga's offices, and we do our own sales besides the production and R&D as well. So our core strengths at Incron, as I mentioned, we are coming from the materials side. So we most often we work with the siloxane-based resins, which we design and do synthesis in-house in here. Also, we do the formulation in-house, and we're targeting to certain applications while we use our own resins and formulations. And recently, quite often, it's been related to optics. Sometimes we do need nanoparticles to boost the refractive index of our materials, but for that as well, we do have an internal source. We are not dependent on any external sources for nanoparticles either. So now what we are also doing is we have a very experienced NIL team. They have a background on the AR waveguide upscaling processes, and what we do, we are offering an optimization of our materials according to the process, or vice versa, optimization of the NIL process for the materials. And the basic idea is to provide the piloting and R&D stage product ramp-up support for our partners. So if I start with the different materials we work with, first of all, what comes to refractive indices. So we are covering a very wide range of refractive indices. Our very lowest refractive index quoting is at around 1.1, and then we go up to 2 or maybe even slightly above 2. That's not now imprintable though, but the refractive index we can reach. So we have cap filling low index materials. We have an optically clear adhesives, and then we have an nano-imprintable resins and high refractive index optical black materials, which I will introduce shortly. So here's another type of the summary of the products we work with. So within this square in here, so we have a high refractive index, nano-imprintable coatings. Within our roadmap, we are coming out within this year with a 1.96, and by the end of the year, we are targeting to have a 2.0 available. We have a matching adhesion promoters.
I
guess
there is a background now. Yeah, we can hear you now.
Okay, so if I just keep on going. So we have adhesion promoters. Adhesion promoters for those nano-imprintable coatings, and then the high index edge blackening, so we can index match the high refractive index substrates to eliminate the non-wanted reflections. Then we have an optically clear adhesive and low RI coatings. And in-house, the main process we work with is nano-imprinting. So as you see on the picture, we work with an EVG tools, but then we work also with the supporting processes, such as an example, inkjet inks. And all this work is targeted to help our customers to work with various sort of applications, such as AR glasses or 3D sensors and alike. Yes, just sort of a standard listing or listing of our standard products. So these refractive indices, which are shown here, those are more or less like a nominal refractive indices. As we do both the resin and the formulation, we can match the refractive index according to the customer requirements. One thing what I would like to point out is this image on the lower right-hand corner. even though our, for example, 1.9 material is nano-imprintable, but it's also gap filling material if somebody wants to do this thing, let's say the other way around. So that's a possibility. For many of these products, or pretty much all of them, they are okay to work with the spin coating, but for some selected products, we also have an inkjettable versions, both at the low refractive index side but also on the high refractive index side. The optically clear adhesives we work, so we have a materials non-filled with the nanoparticles starting from 1.37 up to 1.6, and these are optically extremely good and also thermally very stable. Plus they are gap filling, and it's possible to modify these for the ink shedding versions as well. Then one very important product, we have got excellent results with our customers. What comes to elimination of internal reflections. So we make index matching black materials, and the main reason is that if you have a high refractive index substrate, then at the interface of the substrate and air, or interface of the black material and the high refractive substrate, if you don't index match, you are creating a reflection, internal reflection inside the device, which is shown as a component 1 on the image at the lower right-hand corner. Like a visual demonstration are these 3 green images here. Like on the left, there's a 1.9 index substrate, and the laser light pointed to the edge, and you clearly can see the reflected light coming back around 45-degree angle from the edge. So if we then put the black material to absorb that reflection with a refractive index of 1.5, so we have a delta index of 0.4, you still can see visually that back reflection. And then if we match the substrate index and the black material substrate, it's not visible anymore there. And if you can eliminate the reflections, these internal reflections, for example, with the AR glasses, you see a clear improvement with the contrast of the display, and it's a big improvement. So we're very happy with what comes to this product. Okay, so that was the basic offering we have with the materials, but now we also work with the process. And as I mentioned, we have a very experienced NIL team in-house. So the basic idea is, well, we are coming from the materials side, but what we are sort of wanting to do with our customers is that we can either optimize our materials for the process, or we can optimize the process itself, coming from both directions. We can also discuss and help with what comes to the design, in that sense that we can identify the process limits, so that the design is not sort of trying to overdo it, and we can demonstrate if a certain design can be made either by optimizing the process or the material. Then of course we can do test runs with the approved prototype design, and later on small scale pilot manufacturing, including the index matching edge coating possibility. We have a source for the tool like that for the edge coating. This is the tool we are using currently, EVG, as I mentioned. And here are some examples what we have done with the different refractive index materials, 1.7, 1.8, 1.9, especially at slanted grating. there. It's quite demanding. If you notice, there's a 50 nanometer residual layer, and in that same stamp, there are two opposite directed slants. So it's not the easiest structure to make. And here are some examples where the residual layer, we have been trying to minimize the residual layer, and of course it depends on the structure geometry, but we've been able to get like 30, let's say, depending on the structure, from 30 to 55 nanometer type of the residual layers. Okay, so what Incron is trying to do, we try to link the materials with the process and help our customers to achieve a great devices and applications. So that was my presentation. Thank you very much.
Thank you very much, Jukka, for your presentation. Really interesting. So do we have some question from the participant? Yes, Pavel, please, from Huawei. You're muted, Pavel.
Very good. Thank you for very interesting presentation. And I have a question about gap filling materials.
Yes.
Yeah, you showed you have on top with gap layer, thin layer with same materials. Can you precisely control thickness of this layer on top?
Yes, it's of course the optimization work. So you have to formulate the product like viscosities and the solid content, etc., to match your final approach. But the short answer is yes, but requires a little bit work.
Yeah. And second question, can you print additional grating on top of this grating? For designing, it's very interesting opportunity to make like stack of grating for different, for RGB wavelength, like one grating optimized for green and now for red.
Yeah, in principle, yes, you can. We haven't done that ourselves so far, but I don't see why not.
Okay, no, thank you. It's interesting.
Thank you, Pavel, for your question. Okay, thanks a lot, Jukka, for your presentation. Really interesting. Thanks a lot. Thank you. And okay, the last presentation of this morning by Xavier Bonjour from MicroLED. Hi, Xavier.
Hello.
So this is a use case of Fabulous.
Absolutely. So let me share my screen.
Yes.
That should be the one. Do you see anything?
Yes, you can start.
Okay. So I'm first of all, let me introduce myself. I'm Xavier Bonjour, and I work for a company called MicroOLED, and we do micro-OLED displays. But today I'm going to not talk about micro displays, but I will talk about Active Look, which is a technology we have developed for smart glasses, and also the concept of light augmented reality. Okay, an observation. We looked at the market, the augmented reality market, or what a consultant called augmented reality market. And yeah, we basically think the market has to be split in three segments. Of course, it's not that easy, but at least that gives a perspective. The first segment, it's what I would call advanced augmented reality. That's where you have basically you synchronize the content with the outside content, and that's typically projects and products coming from Magically, HoloLens, and probably Apple. So these, it's the architect. First of all, they're very expensive. They're very efficient, and the architecture is typically what I would call a gamer PC in the glasses. And of course, that has consequences in terms of weight and power consumption. And okay. So advanced augmented reality, that's segment number one. Then we have what I would call basic AR. So typically here, the idea is to have, you don't have SLAM. So the digital content is not synchronized with the external content. And typically the use case is where you put a screen, an existing screen, whether it's TV, a monitor or mobile phone in front of, well, in the field of view of the user. And there are many companies working on that. And then there is a segment which is developing, which we call light AR. And it's, here the idea is to have a very simple function embedded in glasses. So, well, there are three types of products. You've got what we call audio glasses, where you have audio embedded in glasses. So that's the beginning, could be part of the light augmented reality segment, but for sound. We have the product from Ray-Ban, the Ray-Ban stories. So here the idea is to embed a camera and the audio. So that's adding a feature. And I will talk about it. There is the active look technology, where the idea is to have just a display and nothing else. And when you think about it, augmented reality, in the long run, that's the use case which is presented by Hollywood. So you want the SLAM, the advanced augmented reality into normal glasses, into light AR. And of course, technology doesn't allow that. So I guess there are two ways to go to this final product. One, it's the advanced augmented reality. And so you make the final product and you make sure that as the technology makes progress, you can slim down the product. And that's typically the approach taken by the GAFAs. There is also an alternative path, which is to make the glasses people want with minimum technology, minimum features. And as the technology makes progress, you add features in the glasses and you end up in the same final destination. Okay, so having said that, I would like to focus on well, not special case, but a use case of augmented reality, which is part of light augmented reality. You will understand why. It's basically to have mission critical information in your field of view when you are moving, when you have some physical activity. And that makes a big difference, because when you move, then the constraints you have are very different from the constraint you have when you sit on, or just when you stand and do very little. The first constraint is the weight of the glasses has to be very small. It has to be below 40 grams, we believe. And the reason for that is when you move, there is some momentum in the glasses, and if they are not light, well, they either they fall off, or they slide down, or it's uncomfortable. So it's basic physics. You cannot have heavy glasses when you move. Another thing we need to understand, it's glasses, it's a fashion item, so they need to look good, and otherwise they are not going to sell. So that's something you have to bear in mind, because we've seen that in the past, typically with the Google Glass. The design has to be taken into account. Third requirement, the autonomy. Normal glasses, or at least in the case of sports and even operations or even the military to that extent, you need to have a full day of autonomy. That's kind of compulsory for many use cases. Even for sports, people don't want to recharge their glasses, so you need to provide more than a couple of hours autonomy. That's something we found out, which is very important. And perhaps the most intriguing one, it's, well, I'll skip one. It's, of course, the content has to be visible, that's obvious. But the most intriguing one is you don't want the content to be too intrusive. Indeed, as soon as you move, I guess your brain cannot, well, your brain is focused on making sure you move safely, like you step properly, and your visual it cannot cope with too much information. And so we think that having too much information when you are in motion, that's actually dangerous, and the brain cannot absorb that. That's something which is pretty obvious when you that comes from the military, when you have a head-up vision system embedded either in the visor of fighter pilots or helicopter pilots, or even on the windshield of a car, or people know that you cannot put too much information. So that's something you have to bear in mind. Information needs to be very dense, otherwise that's going to be dangerous. And of course, last but not least, you need to provide relevant content, and that's the whole story about use case on augmented reality. Even if you make a very good TV, the use case is going to be provided by the movie. I mean, you need to sell DVDs, you need Star Wars. I think one of the use case we have identified, which is of interest to people, it's sports, because people love monitoring their metrics on their watch, on their mobile, and now on their glasses. So that's, and I'm going to explain a little bit on that. Okay. Yeah. So at MicroOLED, we decided to design a technology dedicated to sports, to augmented reality for sports, because by doing that, we can also address two other segments, which are the military and the operation or the industry segment where you need to move. And so a few words on the key components of the technology. First of all, yeah, the whole technology, it's 6 grams. So that gives you an idea of how dense it is. And of course, we are working on trying to shrink that even further. There is an optical system, and I clearly, well, that's pretty standard. It's a head-up display which is embedded in glasses, and that's where Fabulous, here there are opportunities to shrink this optical system, and field of opportunities here. We have a micro OLED display, and I'll come back to that one later, because that's one of the reasons why we can provide such a compact and such a low power system for these glasses. There is a bit of electronics. There is, it's basically a Bluetooth low energy chips we use to drive the display. The lenses are part of the technology, because where we use spherical lenses, and there is a mirror coating inside, so it's part of the technology. We've added 2 sensors, one which is an ambient light sensor, because we need to tune the brightness of the display to the outside brightness. And there is also a gesture sensor, which is going to be used to interact with the glasses. Just waving your hand in front of the glasses, it's like a touch or a button. You can trigger something in the application. And of course, there is a battery, and we have, with the current setup, 12 hours of autonomy. And if we turn off the gesture sensor, that can be, could be much more than that, around 30 hours. So we explained why we can do that, such a compact form factor, such low power. I think the part of the solution is that we have a micro OLED display solution, which we've designed for that use case. First of all, it's very bright, and normal brightness is about 6,000 candela per square meter. Of course, it can go higher. And that's the standard display. Of course, we have high luminance display, which is twice as much, but we don't need to use that much brightness. The regular display can do the job in the current setup. And another thing is, we have it's low power because we use it's basically a memory display, so we don't need to refresh it. And in the end, that's 1 milliwatt power consumption in normal condition. And I think you may want to put that in perspective with the other types of displays, which some of them been presented today. We have in some instances between 30 to 100 times lower power than other solutions. The other reason why it's so compact is we didn't try to put a mobile phone in smart glasses, because that's, of course, that could be useful, but there are some drawbacks: the weight, the battery, the power consumption. And when you think about it, the use case doesn't necessarily need that kind of architecture. So we basically did, instead of trying to build very smart glasses, very compact, it's just a wirelessly connected micro OLED display. And of course, there is a protocol that enables an application on an external smart device to control the display. But we think that really helps to provide a very compact form factor. A few words on our business model. So we, of course, we provide the technology to our customers, and our customers in this instance are eyewear brands. So we work with the eyewear industry to embed the technology in normal sunglasses and sports eyewear product range. We currently have 3 customers, and it's growing. And we've sold, we do not disclose the numbers, but several thousand glasses already in the past almost 2 years. The other part of the equation, and we think it's pretty important, it's the API. We rely on an ecosystem of partners to provide content for the display. We don't, and it's totally open. It's totally free. So any developer can actually provide content which is compatible with the glasses. So typically here we have a sports application, smart devices, sport watches. So it's currently compatible with Garmin. Of course, we'll be working on the Apple Watch, and we recently announced a strong partnerships with the Shunto, Finnish sports watch manufacturer. So that's for the business model. Maybe a few things on the roadmap. Of course, we'll be working on color displays, and we'll also provide in the coming month a solution which is waveguide based, so that we can accommodate for the prescription, which could be required in some instances. Well, this is a bit of a fun fact. When you look at Light AR, I think, look at the two solutions, which are very different, of course, but there are things where we do think similar between what I would call Ray-Ban, Facebook, and us. The first thing, you need to have a good design. So again, I want to re-emphasize this design thing. It's very important to be successful, we believe. And the other thing, we both agreed that it would be a good idea to partner with an existing eyewear brand. You need to partner with the eyewear industry, and that's something, of course, future will tell us what is right. But we believe that's something which is very important as well. And of course, we do things differently, but I think the market need are driving us both in that case. Okay, so I guess I'm going to stop here in regard of time. Or maybe very quickly, the use case we want to cover with this technology, at least initially, because of course it can go much beyond that. It's the sports use case. So there are new things. Having information all the time in front of you is going to change the paradigm of sports training and sports performance. Typically, it opens new opportunities in terms of coaching. It's very motivating to have information in front of you, so that it's gonna help people to push, to push themselves, and also there will be the possibility to introduce the notion of gamification. There is another one which is very important as well. It's what we call the biofeedback coming from wearables. An example, you have sensors on your shoes. You want to run better, either to get less injuries or to be more efficient because you have a competition and you want to perform better. Having a visual reference which you can modify in real time, that's a great way to modify your typically running techniques in order to either get less injuries or be more efficient by having a stride which is basically more efficient. And that's something which is new and that we are working with some partners. Okay, that was quick, I hope.
It was great. Thanks a lot, Xavier. So interesting.
And, open for questions.
Yeah, for sure. Okay, we have two questions. I have also some questions, but the first one was from Iran Erkan from Morphotonics. Iran, if you want to ask your question by yourself.
Yeah, hi Xavier. Great presentation. Thank you very much. On the 1 milliwatt display, OLED micro display, is there any indication on the price points? I know, of course, these are confidential, but just to give us an idea, one. And number two, in the business model, you show that the optics, the waveguides would need to be done by somebody else. Do you have a reference design for this, or do you have partners that can do this? How does that work?
Okay, pricing. Currently, there are two technology platforms. It's here. Two technology platforms we have developed. The first one, which is I would call generation 1, and that's typically these glasses. We have 3 brands on the market, and the price of these glasses is around 400 euros. Okay. And in the coming weeks, we've announced the platform. But in the coming weeks, you'll start to see this product on the market. So this product is, first of all, it's 6 gram lighter, and it's going to be around, below 350 euros. So that gives you an idea of the price points we are talking about in this market. And to answer your second question, which was, the partners, we've identified some partners, but we cannot disclose them yet. But yes, of course, we have evaluated several partners, and we'll communicate on that, I guess, in the coming month.
Thanks.
Okay,
thank you for your question, Aaron. Thanks a lot. And we have another question from Dipajan Das. Dipajan?
Yes, so I do a lot of sports, and I'm kind of interested to learn more about it because I personally do sports and running and all those things, which also excites me a lot. But I was thinking about, in your business model, you talk about wearables, right? So in this case, what could be the strategy for MicroLED to have some additional wearables on fingers or probably hand, which can be integrated with Active Look?
Of course, we are looking for this kind of opportunities. So typically, I'll give you a use case. Shunto, a very famous sports watch company, and we have a partnership going on where we are going to intimately connect the glasses and the watch so that all the sensors data will be used in the glasses in the best possible way. Of course, you will see the data, but also there will be software to make it more fun, to train you better. So a world of opportunity there. And of course, a ring, anything that goes on the wrist. We are working with a foot pod company as well. Anybody who's got interesting data, which is very dynamic in real time, has some interest, potentially, some interest to use these glasses and to be part of this, of the field of vision of the user where the data is always there.
Yeah, actually, that's very nice. And I have shared a link in the chat about this effortless wearable that we are kind of now launching and working on some MVP. So it would be good to collaborate with you, Xavier, at any point.
Absolutely, I would love that. We can start a side discussion.
Okay.
Of course.
Yes, thanks.
Yes. Perfect. That's really great. Thank you very much, Dipajan. Okay, thanks a lot, Xavier, for your presentation.
You're welcome. It's been a pleasure.
It was really great and interesting as always. So now we can start. Maybe we have 30 minutes till 12. Maybe we can start the discussion, the last part of our workshop, the networking and Q&A discussion. And okay, you can ask every question you have regarding Fabulous, regarding the presentation we had this morning. And maybe to start this, I would like to try to start a kind of round table. Then you can introduce yourself, introduce your company, and why you are interested by Fabulous. So I would like to maybe to start with the first one in my list, Dipajan Das. You asked a lot of questions this morning, but could you introduce yourself and why you are interested by Fabulous, by this workshop?
Yes, I think the main interest is that I'm working closely with the field of AR and VR, and also with a lot of metrology stuff that I'm doing, because from the start of my master's program, I was kind of enthusiastic about developing the light engines for smart glasses, and my thesis was based on that. And then I'm interested about how this kind of freeform optic stuff can be integrated, like for combiner optics and probably different kinds of displays, because now we are looking into different factors of like field of view, then comfortability, then weight of the glasses, and then the processing power. So that's the reason. And then also some kind of interaction tools with these smart glasses so that we can have very good point where we can interact with these glasses, and also we can try to integrate them to our lives.
Mm-hmm.
So it might be related to sports, or it might be related to some other use cases. So it's very interesting for me.
And did we get some answers this morning? Did you get some answers for your question this morning, Deepajan?
I'm not getting you.
Did you get some answers this morning?
Yes. Okay. I got a lot of answers and a lot of interesting presentations from all the way around, and everybody. I'm kind of thankful for Morphotonics, Huawei Technologies, Incron, MicroLED, Epic for making this very good webinar discussing the challenges, and also to ST, Bharath, for introducing their unique solution. Then I was happy about TriLite because they are giving this LBS modules in very small form factors. So it was kind of like a totally very good knowledge about how the industry is moving towards these smart glasses.
Thank you, lot. Thank you for your feedback, Deepajan. It's great. Is someone from Huawei would like to come on this workshop? You are 3 in the room. Would you like to take the opportunity to say something? You are 2 now. But Chen. Oh yeah, Pavel.
Okay, maybe I can talk a little bit. Yeah, it was very interesting for me, and was to see some opportunities to use. Especially for me, it was interesting to look at this opportunity for large scale nano imprinting technology, because we have project where we would like to use these possibilities to fabricate large scale waveguides.
Great.
Yeah, thank you.
Thank you.
Yeah.
Yep.
This is Fernando from Huawei too. I also want to thank people connecting us during this workshop. So this is, I think, the target of these events. So is deploying the actual technology and also networking. And this is why we are here. So we were to do advanced products, and I think this is the way to, and the forum to do it. So thank you.
Thank you very much. And did you were interested by Fabulous especially, or it was mainly for networking this morning for you?
Well, I've heard about that. So and received invitations. Well, mainly from Pavel was the one that I think he was in any kind of event before. I also have heard about it, especially from LIMBAK. People I have some connections in the past, and well, yes, I suppose that this is a platform we can use, and we can be in contact in the future.
Yes, we have Jessica Van Reyk here. Jessica, if you want to add some information, you can.
I mean, of course. I mean, for sure, it will be interesting to contact later and see how we can collaborate and what you are looking for and how Fabulous can possibly assist you with that.
Mm-hmm.
Yeah.
Maybe short question. That website mentioned like all European countries can participate in Fabulous project for international companies like Huawei. Is it possible?
So anyway, Fabulous can help. Just there might be some restrictions on getting funding. So then we kind of expect the office to be in one of the eligible countries that the European is providing this funding for. But in either case, Fabulous is open to all.
Yeah, just a remark, because we are Huawei Technologies in Düsseldorf, so we are German company. So another thing is what are the criteria in order to select how is the helps, etc. But legally, we are as another European company.
Yeah, so let's look into that and see how that affects you specifically in terms of funding. If I would have to double check because I'm assuming that the headquarters is maybe somewhere else, but you want to apply maybe from the German office, then I can double check with the project coordinator to see how that affects the possibilities for funding. I would have to double check.
Mm-hmm. Thank you.
Thank you for your interest a lot. So do we have other interesting people in this in the room? Maybe Rudy Ablinger from Sony. Do you want to give us a feedback of this morning and why you are interested by Fabulous?
Hello, yeah. Nice to all meet you. Thanks, Jeremy. Yes, we are scouting the micro optics market for some time already. Gerald and my colleague from engineering side and on the business side. Why we are doing this? Sony DDC here in Austria is a disc manufacturer. So we are one of the exclusive PlayStation 4 and 5 manufacturer. And the existing technology we do have here around polymer injection molding and nano imprinting and various processes for coating. We want to look and leverage how to accelerate this for micro optics. At the moment, it's a market study and feasibility project. So we are connecting with the network, with EPIC and the members, and try to find out more of your expertise that helps our feasibility study to grow and become more mature. And of course, Gerald and his engineering team is also working on fabrication processes, a lot of in theory, but also we are working on some prototypes but this is with existing disc manufacturing technology. But so it's a kind of bridge from where we are today to maybe where we are maybe tomorrow. So that's what our core interest is with this EPIC and all the Fabulous initiative as well. So very interesting, very helpful for us at this stage.
Great to hear this. Thank you very much, Rudy, for your feedback. Great. And Marivan Chaloni from Synopsys, do you want to introduce yourself? Yeah, hello.
Hello, yes, my name is Marivan Chaloni. I'm an application engineer at Synopsys. Really nice discussion over the morning. Thank you for coordinating those discussions. And yeah, I see a lot of new, let's say, more compact design for ARVR. It's nice to see that. So we know that we need to go in that direction to bring this type of component on the market. I really appreciate the demonstration of Xavier from MicroLED or also from ST Bharath, really nice. And on our side at Synopsys, we are providing software, optical design software, so a solution to help optical designer to bring or to overcome with all the challenge that they have at the point of the design, from the micro LED design itself up to the gratings that are involved in the goggles and how to image the picture on a high with the quality of the picture. So yes, I know quite a lot of the company who are joining, and it's really important to be involved and to know in which direction the market is going. And in case that any of you has design challenge in terms of the macroscopic level or at the micro scale of the micro lens itself, the freeform design, of course, Synopsys is clearly a partner for your design process.
Thanks a lot, Marivan. Thank you for the introduction. Great. Anyone else who wants to introduce itself? Maybe I would like to ask to Alperen Aydin from the Tampere University. Would you like to introduce yourself and why you were interested by this workshop? Alperen, are you here? No. Okay. Marina, are you in? Marina Postnikova from Phasics.
Hello.
Yeah, hello.
Hello. Thank you for interesting presentations. Phasics is a company we specialize in optical metrology. And so particularly in this session was interesting for augmented reality or virtual reality applications. So as it's involved like free space optics, for example, we do a meta optics characterization. It's interesting in this way for us. And also just any challenges where in this field could be applied the optical metrology, for example, not only for characterization optics, but alignment is system testing of all components in the virtual reality setups or glasses. Yeah.
Thank you. Yes. And you will be here tomorrow morning for a presentation.
Yes.
Thank you.
Right.
Thanks a lot, Marina. Any other people? We have still 5 Elisanda Lara in the room. Maybe they would like to introduce themselves. I don't know. If you have some question about Fabulous, it's still the time to ask.
Sorry, I have one question. Sorry for asking so many questions, but
that's cool.
I'm very curious about something. But is Fabulous Line supporting startups as well, or do you have some kind of incubator programs that support startups?
Well, yeah, so we have this funding available right now. So that's available for startups. Actually, smaller companies are eligible for quite some funding because the idea is to support also these innovative solutions at startups and smaller sized companies. Although the open call is open to all companies, it is, however, very much aimed at making the bridge between prototyping and large volume manufacturing. But we can support also with prototypes.
Okay, that was a great answer. Thanks. I will contact you.
Thank you. Looking forward.
Maybe Jessica, you can put again your email address in the chat if they want to contact you.
Yes, that is a very good plan. Of course, it will be in presentation and it's on the Fabulous website.
Andrea Lovera from the Femtoprim, do you want to give us your feedback and why the reason you are here?
Yeah, so Andrea Lovera, I'm the CTO of Femtoprint. So I joined the meeting because, first of all, we have recently hired Mr. Rolando Ferrini, which is sort of the father of Fabulous. So, and we are a company offering an enabling technology for micro optics and mastering. Therefore, it's interesting to keep monitoring what's going on in the field. So we provide glass components with micrometer precision in 3 dimensions. We can do freeform design, standard design, and also integrate this feature into more complicated devices, integrating fluidics, optics, mechanics eventually.
Great, thanks. Yeah, thanks a lot.
You're welcome.
And Guillaume, you have a question? Guillaume Tison from Imagine Optic.
Yes, please. I wanted to ask Fabulous about their metrology capabilities. How fine can they measure what they produce, and if they can develop on the metrology challenges that they feel are going to happen in the near future?
You are muted, Jessica.
Yes, so we have a metrology partner that is doing the metrology right now for the use cases within Fabulous. I'm, however, not able to tell you exactly what the precision is because I've not been involved in this process within the use cases. My technical coordinator, Tom, should be able to answer that. So if I can come back to that later, then I can provide you some more insights on that.
Yeah, we can put you in contact, Guillaume and Jessica. Great, thanks a lot. Any other question about Fabulous, about the presentation this morning? Ishwar from KTH, you want to introduce yourself? Okay. Okay, yeah, Marina, please.
Yes, I have quick questions to the Fabulous. On your website, there is different applications market as main markets, automotive, ARVR, but also different more small markets like for daylights, PV, or security and branding. And I see that this one, like your priorities, or what is, I understand that automotive is now, let's say, more potential market, but what the distribution between all the markets you put your effort in the, I don't know, technologies and the fundings?
Well, so for the funding, we would actually like to have a really broad spread. So I welcome any markets. I would actually like to see a lot of markets, and we are also actually seeing it. So if I'm looking at the spreads from the context that we've had so far about the services that we offer, we see also that it's coming from various markets, and I think this is good. So it shows that there's a lot of markets looking into this now.
Okay, nice. Thank you.
Thank you, Marina, for the question. Okay, so maybe we can end this session, this workshop. Just would like to thank all of our speakers and all the participants. We were almost 40 this morning, so it's quite great. So thanks a lot for your question, for your interest. If you have any other question, please ask to Jessica. You can also send me a message, and I will put you in contact with Jessica. And maybe Jessica, if you have some things to say, the ending words, I'll let you say something.
Yes, then yeah, micro optics is fabulous, right? So that's what we are aiming. We are here. So if you think micro optics, think fabulous.
Yeah. Thank you very much to all, and see you soon. Bye-bye.